recording. Yeah, cloud is good. Yeah. All right, so I'm happy to introduce or reintroduce our speakers today. Bill Bialek is the founding director of the Initiative for Theoretical Sciences. He is a visiting scholar presently. He's an expert. Well, I'm not sure an expert. Like one of these things where a person is engaged in multiple fields. He enjoys contributing fruitfully to several fields across the interface between biology and physics. He's one of the sort of agenda setters in that field, and we're fortunate to have his sort of insights here today. David Schwab is CUNY faculty and a member of both biology and the physics departments, physics programs, and he will be giving the second sort of part of the presentation. Okay. And did we decide?
Yeah,
Yeah.
you should wait.
Thank you. Wow.
That was your excellent introduction. So we're a small enough group that people should interrupt. I think both David and I, there are things we'd like to say, but if we say a little less and you understand more, that's also maybe even better. So we chose, that's too much. It's an intimate group, but not that. Okay. So we chose the well, okay, so first let's get oriented. I don't know how many of you have actually visited the Nobel Prize website. You might think it's only for the general public, but it's got fantastic stuff in it. So in particular, there's a kind of report from the Nobel Committee, which is called Advanced Information, which is their take on, what it is that's being honored by them. And our title, Moving the Boundaries of Physics, is actually taken from the second line of the report, which notes that with this prize, the boundaries of physics have been extended to encompass the phenomena of life and computation. So it's a very explicit recognition that physics is a much broader effort than it was even in the recent past. So there's a site, it as those of you who have visited know, it also eventually accumulates biographical information about the laureates and so on. You'll also see that the Nobel Foundation does quite a good job of reaching out to the general public. So that isn't what we're there for, but it's something to appreciate. These are our heroes, Jeff Hinton and John Hopfield. And so we decided, so the work that is recognized by the prize is essentially complete by about 1986. And it obviously has this enormous resonance today because of the tremendous revolution in artificial intelligence that we're living through. And so we decided to divide up the task. I'll tell you about things that lead up to 1980, that go through 1986. So the period of the things that are actually honored by the prize. And then David will tell you how we got from there to here. I think he has a much harder job. But let's get started. Interesting. It must be your fault. Okay, good, that works. We can do that. Okay, so let's get started. What's the origin story? So as many of you no doubt know, John Hopfield started his life doing condensed matter physics, or as it was called in those days, solid state physics. His PhD advisor was Al Overhauser. Some of you will have heard of the Overhauser effect in nuclear magnetic resonance. Probably should have gotten the Nobel Prize for that, but he didn't. John's PhD thesis produced exactly one paper, single author. He has in one of his autobiographical essays he talks about the great gift that his advisor gave him of giving freedom to work on his own. And he hopes that he's been able to pass this along to the next generation of students, which I think means that he also lets the students wrote papers without him. And in the background, there's some hint that maybe being hands-off isn't always the best thing, but John's thesis has this slightly complicated title. The basic idea is that in solids, you know that, yes.
You can stay closer to the mic.
Yeah.
It's actually a really good mic. Yeah,
I
so
see.
maybe we can feel it.
Well, no, if you do that, then it has more chord. Okay, I can try this. You know that when light propagates through an insulator, you can excite the electrons and you leave a hole behind. And you may know the electron in the hole can bind to form an exciton. So in the 1950s, the idea that you can have excitations of a system which are not the same as the microscopic degrees of freedom, that was an idea that was emerging. And what John did in this paper was to show that actually you can get mixing of the excitonic mode with the propagating photon itself. And that combined excitation is called a polariton. And 35, 40 years later, people started to be able to produce large numbers of polaritons. They're bosons, so they do a kind of Bose-Einstein condensation. The whole field had a sort of resurgence in this last generation, which is quite remarkable. Jeff, so we're going to have to think about how John got from thinking about solid state physics to the things that eventually the prize is awarded for. Jeff started out doing what was already described as artificial intelligence, but it of course meant something very different. He was trying to his thesis was about problems in, broadly speaking, computer vision. And he introduced a set of methods which have, although the notation is very computer sciencey, the intuition is very physicsy, which is that when you're trying to interpret an image, there are sort of many things you're trying to get right. You're trying to actually fit the data that you have. You're trying to obey constraints of the rigidity of objects, the smoothness of their boundaries, and so on. And that you can think about the dynamics of an algorithm that satisfies these constraints as relaxing as it gets pulled by the different constraints. He doesn't actually write down an energy function in his thesis, but it's almost there, right? Which is a very modern point of view. Jeff's PhD advisor, by the way, was a fellow named Longat Higgins, who obviously spent a fair amount of time thinking about artificial intelligence, but that was late in his career. He started life as a theoretical chemist, and in that capacity discovered one of the first concrete examples of a geometric phase in quantum mechanics. So the physics roots of all this are quite deep. That's his brother. Yeah. Yeah. So they were in school with Lighthill and Dyson. There was, anyhow, yeah, there's a story there. Wikipedia is useful on that one. Good. So how do we get, I don't want to give you an entire biography, but it is interesting to ask yourself how it is that somebody who was thinking about the interaction of light and matter, or light and electrons in solids, found his way to thinking about brains and memories and so on. And I've known John for a long time, and at one point I asked him explicitly, how did you decide to change fields? And his response was up there. I didn't change fields, I just kept doing the same thing, and the fields moved past me. Now, that was a rare moment, I think, of false modesty. But it is true that if you read the papers about solid state physics, and then you read certainly the starting papers as he moves into thinking about the physics of life, there is a strong intellectual coherence to them.
and he has a definite theoretical style. He's not the kind of theorist who does very complicated calculations. He's rather one who sees his way to doing the simple calculation that actually gets to the point. In the background, there might be a complicated calculation, but he's not showing off. In the 1970s, he got interested in biological problems, and in a very short period of time, I'll draw your attention, this paper, which is not his first on biological problems, but sort of it's about 2 years after he started, and it's kind of the culmination of his thinking about protein structure and dynamics. That's the 11th of December, 1972. And this one, which I'll explain in just a moment, is August 6th of 1974. So in this roughly 2-year period, he touched this very wide range of problems that are roughly speaking at the molecular scale. So this is trying to understand in a large molecule, how is it that when a small molecule binds in one position, it has an effect very far away? So how is information transmitted through the protein? And the picture that he arrived at was one which we would all find as physicists very comfortable. It's a picture of extended modes and so on, which was very much not what people were thinking at the time. And also in keeping with his style, which was harder to do once he started thinking about neural systems, but he pushed it as far as he could. There's this intimate tie between that abstract picture and direct experimental probes of the molecule using different kinds of spectroscopy. It's a very elegant paper. And actually today, there are many people in the soft matter community who are interested in this problem of allostery. That is to say, well, how is it that when you do something over here, it influences something over here? Allostery means other site. And the things that they're doing today are actually much more closely related to what's in Hopfield's paper than to any of the other papers on allostery from that foundational era. The next topic was, and there is a thread here. So this is thinking about one molecule at a time and actually thinking about what's happening inside the molecule. Now you start thinking about how molecules interact with each other. And one of the things that's absolutely crucial, particularly for the early events in photosynthesis, is that electrons can be transferred from one protein to another. And there was rampant confusion about how much of that was quantum and how much of it was classical. The dramatic observation is that you can cool things to liquid nitrogen or even liquid helium temperatures, and the electron transfer reactions proceed more or less unimpeded, which made everybody think there was tunneling going on, but it was confusing. And so this paper sorted all of that out. The electrons always tunnel. The atomic displacements cross over from tunneling at low temperatures to thermally activated motion at high temperatures. And where that border is depends on the internal dynamics. And there are actually now examples where the border is pushed up toward room temperature. Finally, perhaps John's most profound contribution, many people would say even deeper than the thing for which he just received the Nobel Prize, is kinetic proofreading. So if you ask, why is it that you look like your parents? The answer is that the genetic information that's encoded in DNA is passed faithfully from one generation to the next as the molecule is copied. How does that work? Well, if you had a good high school biology course, you know the answer. The sequence of A's, T's, C's, and G's can only bond with the complementary bases, A with T, C with G. And there are echoes of this in other molecular copying processes throughout the life of a cell. What John realized was that the free energy difference between making the correct and the incorrect base pairs was large, but not that large. In particular, if you let a dangling A base come to equilibrium with all the other possibilities, the probability that you get the wrong base pairing is 10 to the minus 4, which seems pretty low, but you have 1 billion bases in your genome. Experimentally, the error rate is 10 to the minus eighth. So what, to say it in modern compact language, cells are succeeding in sorting the bases with a precision which is far beyond what is accessible in thermal equilibrium, which means they're essentially building a Maxwell demon. And you know that the solution to the Maxwell demon problem is that you have to dissipate energy. So this paper is a masterful survey of many different biological processes in which this problem arises, which were the subjects of different literatures, and then sort of digging into each one, figuring out where the energy is being dissipated, and showing that that actually allows for this increase in accuracy. And there are two important things about this. One is, it really is the answer to why you look like your parents. The answer in your biology textbook doesn't get you there. And relatedly, if you want to imagine what life would be like without proofreading, you can think about HIV. So HIV is a virus that doesn't proofread when it copies. And that's why the virus evolves so quickly in a patient. So life really would be qualitatively different were it not for kinetic proofreading. Relatedly, it represents a transition from thinking about what one molecule is doing or understanding the rate of one particular chemical reaction in terms of the underlying protein dynamics, to thinking about a whole network of reactions and how they function together to produce, in this case, enhanced reliability of information transmission. Okay, so it's this moment of transition from sort of single molecular events to something a little bit more collective. And that, of course, is going to be the message of the work on neural networks. And in the interests of both informality and clarity, I'm going to try and do most of that on the Blackboard. So the classic problem of Maxwell's demon is you're sorting molecules. So in the simple case, you have a container, you have a wall between two halves of the container, and the demon sits there, and when it sees a molecule moving very quickly from the right, it opens a trapdoor and lets it go in. When it sees a molecule moving slowly from the left, it lets a trapdoor, opens the trapdoor and lets it go through, and if not, not. And if this process continues, you'll end up with all the fast-moving molecules on one side and all the slow-moving molecules on the other side, and that means you will have created a temperature difference, and so you can do work, thus violating the second law of thermodynamics, because you started with a system at constant temperature, at a single temperature. So in order, on the other hand, you can certainly imagine somebody there opening and closing the door, so what gives? And the answer is that the demon had better expend in this process as much energy as you could gain from the temperature difference that he created, or else you will violate the second law of thermodynamics. And so that's the sort of abstract version of it. And then there's sort of digging in, where does the energy get dissipated and so on. But that's the general principle. You can sort molecules to a precision beyond what's available in equilibrium, but only if you pay for it energetically. So it's fascinating question. So quite a bit was known about the molecular events responsible for copying DNA, for reading out the DNA into messenger RNA, for taking the transfer RNA molecules that are the sort of physical embodiment of the genetic code and getting those built with the right amino acid, with the right codon for things that happen at the ribosome. There was stuff known about all of these biochemical reactions. And the steps which allow for proofreading were known. What wasn't understood was that there was a general problem and that energy dissipation was essential. So in the account given in this paper, the motivating experiment is just the observed precision. It's not, oh, why does this reaction happen? Because that kind of leads you nowhere, because you can point to all sorts of things and ask, why does that happen? And then the biologist will tell you you're not allowed to ask why. That's just the way it is. And so the motivation is really a very macroscopic experiment. You know, what is the frequency of mutations in when a bacterium replicates? Yeah.
Maybe CRISPR can be something similar to CRISPR, like
So there are questions about precision there, which I'm not expert on. So I'm going to punt. And of course, just to complete this, right? There was in fact, John himself started to work with experimentalists to get direct evidence for proofreading. One of the world's great enzymologists spent, a decade of his career sorting this out in one class of problems. And in what, to my mind, is the most beautiful of the modern physics experiments with single biological molecules, you can watch a single molecule of the RNA polymerase walk along the DNA. You can measure its displacement with an accuracy better than the distance between single base pairs. So you can actually see it go click, 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 click. And you can then feed it the wrong nucleotides and watch it back up and correct its mistakes. Well, you can't quite show that it's correcting its mistakes, but you can show that it backs up. So you can literally see it proofreading. That took a long time. Yes.
So, I mean, I guess the sense I have generally is that there's a cultural sort of a cross-fertilization in some sense, because, putting the numbers in and trying to say, oh, that error rate is too low, something it
Yes.
not be there by itself in the thermal environment. Is that kind of a sort of a physicist, sort of a not minding that, coming to biology and saying that can't possibly happen by putting the numbers in? Is that John's sort of was John on the forefront of that, or people?
So, look, the history, this is not the place to tell the whole history of the interaction between physics and biology. What I will say is that in that long and rather complicated history with lots of give and take that reaches back into the 19th century, I think in that era, sort of 1970 plus or minus a decade, John was the one who had the clearest vision of what a theoretical physicist's engagement with these phenomena might be like. And it was different in different examples. There's an attention to the numbers. There is attention to the details of experiments. In the kinetic proofreading paper, he really goes into multiple biochemical literatures, and he had very good tutors in doing this. So he sought out people who could advise him. But at the same time, there's sort of this lifting up from the detail to try to understand that there's something general going on. It was very inspiring to young students at the time. So before we dig into the real meat of what happened to lead to the prize, so that was prologue, right? So you can imagine him going from thinking about solid state physics problems, sort of drifting through different aspects of the biological world. And, you don't need a motivation to think about the brain, but maybe you need some warm-up exercises to convince you that you can get all the way from thinking about light and matter and solids to thinking about the brain, and that's what he followed. So before we dig into that, I want to remind you of some basic facts about emergent phenomena in simple models. And of course, also in real materials that these simple models describe, but let's think about it in the context of the models. So if I write down the Ising model, in which I have variables that are plus and minus 1, spin up and spin down, they can interact with their neighbors. The energy is lowered if the spins are parallel, raised if the spins are anti-parallel. You know that model, so that model as written has a symmetry. If you take all of the spins and flip them upside down, then the energy stays the same. And the ground state of the system breaks that symmetry. They all point in one direction or the other. They don't do some complicated superposition. But that's a discrete symmetry. And in some sense, you can think about that as you're getting ready to think about what Hopfield did in neural networks. You can think that the system is capable of storing one bit. So you put n spins together, where n is very large, and together, depending on their initial conditions, they can all decide to point up or point down. But only that one bit. They don't do other interesting things. Robust. On the other hand, if the spins that live at the lattice sites and interact with their neighbors are little vector spins, right? So in the simplest case, just unit vectors, then they can point in any direction. But the statement that the symmetry is broken now is that they will all point in the same direction, but that's a continuous choice. So that direction could be anything in 3D. So what that means is that the system, as it chooses to fall into one ground state that's effectively disconnected from all the others, it stores a variable which is just the direction on a sphere. Okay? So it's one direction in space, still one variable. Many of you know that, okay, I can't resist walking around, but I'll be sure that I talk louder in relation to the microphone. Or maybe, that should help a little bit. Many of you know that if instead of having spins that just interact with their neighbors, all the spins can interact with each other. And furthermore, the interactions are themselves randomly positive or negative. That's called a spin glass. And the mean field version of this, where they can all talk to each other, I mean, in a real material, presumably the interactions are still local, but if you imagine a model in which they can all interact with each other, that model has many, many locally stable spin configurations. And so in some, it's the thing which is the order parameter is a function, not a number. And so in some sense, it's capable of storing an infinite number of states. The problem is that there's no way to tune the connections Jij, the interactions Jij, to program in the states that you want. So it's as if you had a memory with a very high capacity, but you don't, if I give you a configuration and I say, store this configuration, you don't know how to do it. These aren't the only examples of ordering that we have in condensed matter physics, but they're sort of typical. They're classical. We can discuss whether anything changes significantly when we think about the quantum case. But what I want to prepare you for is the idea that neural networks are a new class of emergent phenomenon, precisely because in a system with n model neurons, you can store n states, order n states, but there's a way to program them. And if you think about that, it is the model that you're going to write down is indeed a model that looks like this one, except the actual interaction strengths Jij that you get are strongly atypical in the random ensemble. And so normally, we could say, well, it's okay if you choose them at random, and it's okay if they all happen to be equal because of translation invariance. But to have them be finely crafted so that something works, usually we don't like in physics. But if you're making a model of the brain learns. And through that learning, you can stabilize a collection of highly atypical parameter values, which then produce this new class of phenomena that you wouldn't see otherwise. So let's try to do this. And what do I want to do? Yeah, maybe the simplest thing is to turn off the projector. So if you go into the brain, you'll find neurons, they're cells, right? They're discrete cells. They have the body of the cell, let's say, has dimensions of order 10 microns. And the cell has long processes that come out of it, and it has a tree of places where it takes inputs. And if you record the voltage difference between the inside of the cell and the outside of the cell, you see discrete pulses, which are called action potentials or spikes. And this is often described, was originally described as saying that neural responses are all or none. So what that means is that from the very beginning, and from the very beginning means, 1920, it's understood that if you look in small windows of time, then you have a binary variable, which you might as well describe as being a spin. So that happens naturally. Now, how do these things interact with each other? Well, it turns out if there's another neuron here, its output end can make a branch and connect to this one. And so if this is neuron J and this is neuron I, there are many of these neurons. And indeed, if you look in the central regions of your brain, a single neuron is taking inputs from several thousand other neurons. And there are special places where it's 100,000. And very early on in the 1940s, people tried to write down a model that captures the outline of this. And so the pioneers here were McCulloch and Pitts. And what they said was, well, if I look at neuron I, let me go in discrete time steps, and I ask what happens at time t+1, you could say, well, this neuron is getting inputs from all the other neurons. And in the simplest case, let's imagine that it just adds them up. So if you want to, every time an action potential from neuron J arrives at this connection, and these connections are called synapses, every time the action potential from neuron J arrives at the synapse onto neuron I, it effectively injects a little bit of current. And we understand how that works, but it's not essential for what happens next. And those little current pulses get added up as they flow into the cell. Each of them occurs with a different weight, both because there might actually be something happening at the synapse that sets the weight, but also, of course, because they're in different places, and the impact of current in different places on what happens here is different just because of the geometry. Remember that neuron I also has an all or none response. So it has to take this input and compare it with something to decide whether to be on or off. And if you buy that what it does is just add everything up, then you're sort of stuck. There's only one thing left to do, which is to compare that through a threshold and then take the step function, or sorry, we're in plus or minus 1. So let's take the algebraic sign. And that's the model. So what did McCulloch and Pitts do? What they did was to show that if you fiddle with the JIJs enough, you can do anything. So remember, this is 1940s. This is after Turing provides us with an abstract view of what it means to compute, but before anybody's actually built a computer. Yes. Theta I is a threshold. So you sum up your inputs, and you have to decide whether to turn on or off. So in general, you could compare to 0, which is the simplest thing. Just ask, is my input positive or negative? But more generally, you could compare it to some threshold.
It can happen that in a real biological system could be directionally dependent on where the current is.
So it is in most of the brain of most animals, although not at all in some animals. So you have to be careful. the statement that what neurons send to other neurons are these discrete action potentials is essentially exact. Now, it is true that the shape of the action potential can be modulated, but that's a slow process. And it is true that in a sequence, the shape can change, but that's typically because they've gotten too close together in time. So in some sense, there isn't any extra information contained in the shape. Now, you might not, in order for this to be binary, you have to look in very small time bins. And that might not be what you want to do for a whole variety of reasons. For example, it might be that the neuron itself is integrating over a longer time. And so thinking 1 times, 2 milliseconds by 2 milliseconds is the wrong thing to do. So the way in which you need to depart from this is mostly about timescales, as opposed to a violation of the intrinsic discreteness. I think that's fair. Yes. So if you inject current here, and you look here, then either you see an action potential or you don't. And the action potentials that you see all look alike. So there is an intrinsic discreteness to the response. Of course, this response can occur at any moment in time, which means your chopping things up was a little bit arbitrary. Yes.
Feel free to ignore this question because it's going down the rabbit hole. But it's not actually the action potential that's communicated, it's the release, it's synaptic vesicles.
Correct.
And so is this model just basing it, is it simplifying it and saying the activity of the presynaptic cell passed in terms of action potential is what we're going to model, and it's ignoring the translation of that into chemical release and everything else?
So, not a rabbit hole. Okay. Okay. Of course, this is oversimplified. And, McCulloch and Pitts already knew it was oversimplified in 1943, and we know more now. So, and none of that's in there either. So what you're saying is, well, let's think about what actually happens at a synapse. And what happens here at a synapse is you take the action potential, you multiply, the presence of the action potential adds something to the activity of the neuron on the other side of the synapse, and that happens instantaneously. So, but it happens with a coefficient. So now, we know, as you point out, there's this process in which discrete vesicles are released, the content spills out of the synaptic cleft, it diffuses across, it binds to a receptor. In many cases, the receptor directly changes its structure and acts as an ion channel, effectively injecting current into the cell, although it's not a current, it's a conductance. So the actual current depends on what the internal voltage already is, and I could keep going. So for example, since what you do is you open a channel, then the current that actually flows depends on the difference between the voltage outside of the cell, which you could say is relatively constant, and the voltage inside the cell. But the voltage inside the cell relates to what's been going on inside the cell and all the other inputs. So there's a natural path for something that's more nonlinear than what you're writing down here. And in order to get that right, you'd have to smooth things out over some time scale, which is the time scale on which these transients are rising and falling.
But the information that's being modeled here is being for this model in the action potential.
Right. Well, okay. So let me make one more observation, and then we'll close. We'll leave the rabbit for the moment. There's another view which says that neurons can be active or they can be silent. And that statement about activity might be a bit more coarse-grained. So to give a concrete example, there are many neurons that have a pattern in which the action potentials come in bursts. And so maybe what I mean by spin up and spin down is I'm in a burst, I'm not in a burst. And then that's something that's more extended in time. And so even if you write down the same model, you've sort of averaged in a bunch of slower processes. So it isn't completely clear. I introduced the action potential as the motivator for making things binary, because that's where McCulloch and Pitts started. Also, I happen to like that view myself, but it's as you back away from looking at every action potential, you can retain a binary approximation. But then the thing that you're describing is more sort of extended in time.
They have enough, it's natural on nowadays. So you have enough of the.
Yes.
In
Yes.
the reasonable assumption nowadays.
It's still not terrible. And in some sense, you can tell that it's not terrible because making good measurements to show that it's not true is still interesting. Right? It's not that it's true, but that giving a good characterization of the way that it's not true is a perfectly sensible research program. Which means that it's not a crazy assumption, right? If it was crazy, then you just have to find some other place to start.
So there are no experiments.
Oh, you can convince yourself quite easily that the summation is not linear. And so but what people try to do, for instance, is to say, well, maybe it's linear in this region. And then something nonlinear happens. And then that nonlinear thing from this region and this region are passed. And so you could say that inside one neuron, you have a couple of layers of this kind of processing. Yes.
Just, you literally just said 2 words about this. If I understand correctly, the impact of McCulloch is not to oversimplify it or simplify it just right. It's really connecting to querying computability.
So, right. So let me pick the thread back up.
No, but
Yes.
then the question, my question, practical question would be like, suppose you take whatever your favorite nonlinear, biologically relevant version of this, do you compromise the computability or not? Right? If that's really the impact.
So that hasn't. Actually, I'll give the correct answer, which is I don't know. I think there's a longer conversation to be had there. I'm not sure I have much to contribute to the conversation. But so, as I say, McCulloch and Pitts comes between Turing giving us a picture of what computing is and a formalism for thinking about it and actually building computers, which is an interesting moment. And so that means, by the way, that the guys who first built computers knew about McCulloch and Pitts, right? So there's some interesting history to be traced there. And the goal that McCulloch and Pitts set for themselves was to show that even just with this cartoon of what real neurons were doing, you could compute anything. And so they succeeded in doing that. I don't know whether we would say they proved a theorem that's a Turing machine, but okay. There's a beautiful title. The title is beautiful. The logical calculus immanent in neural circuitry or something like that. It's a very, they were very ambitious. The problem, of course, is that if I tell you that by choosing the right set, the right matrix J, you can do anything, I can predict nothing. So if I give you a real brain and ask you what it's going to do, the answer is, well, it could do anything. So in order to make any progress, you have to make simplifying assumptions about what the JIJs are. So I think if I go too far down, we lose things. So I'm gonna. So. Oh, I see. Okay. So let's simplify down here. Yes, there's room at the bottom. Maybe not the bottom. The question isn't whether there's space, right? So in order to make progress, you have to simplify the JIJ, and that's so one idea of how to simplify is that if there's a connection from neuron J to neuron I, then there is no connection back. And so the network is completely feed forward. And with a little bit of luck in your description of the network, that means that you can think of it as a set of layers in which these things now have arrows. And you can think about iterating them. And so architectures like this are called perceptron. And they appear circa 1960, plus or minus. And to give you a sense of how the exploration of things that we now call artificial intelligence is intertwined with the physics community, if you want the great reference about perceptrons, you can look in reviews of modern physics. And the idea was, I have inputs, I do this trick of taking weighted sums and thresholds, and in the process, I pick off features of the inputs, and then I take features of the features and so on, and eventually I would see, right? I would recognize objects. Yes? So each unit here does this computation, and what lives on these arrows are the JIJs. Thank you. It is a feature of this field that people draw pictures which are disconnected from the equations. So sorry, I've fallen victim to it myself.
Okay, and the layers are.
And the layers is just to organize things that since there's never a backward connection, right? If I connect to you, you don't connect to me. So that means that in some sense we can stand in some order, right? Now it's a little more to say that everybody can stand in order. So there's a whole set of people at my level who talk to people at your level, and you talk not back to us, but to the next level.
We have a bunch of neurons that talk to other bunch of.
Right.
Therefore, there are only two layers.
Well, ... You can imagine more. So in the beginning, people were hoping that they could make progress with a small number of layers. Because I don't know whether David's going to show a picture like this or not, but there is a marvelous thing you can do, which is to, which we did in a review article, a student and I, is to take a picture from 1960 in Reviews of Modern Physics and the 2015 review of what can be done with deep neural networks, and put the two pictures side by side. They look the same. It's just that the deep networks have many more layers. This is a little bit off the beaten track, but I wanted to emphasize that what's essential is to simplify the matrix JIJ. So you should think of the perceptron in relation to McCulloch and Pitts as one of the ways of simplifying. There's another way of simplifying.
There are no loops, right?
No loops, yeah. And we all know in statistical mechanics, it's the loops that make things hard. Yes.
What is that realistic in the action?
Interesting question. It's something people argue about a lot. So completely feed forward, surely not. Approximately feed forward, and maybe feed forward over sufficient time windows, right? I mean, there might be feedback, but the loop might be long. And so depending on what question you're asking, maybe you don't need to think about it. We now are just starting to see complete connectomes where you have the entire map of synaptic connections among neurons in a chunk of the brain, or in the case of a fruit fly, in the entire brain. And large portions of that are approximately feed forward.
That, regardless of any sort of recurrence or feedback and so forth, in the day that the constant input of sensory information.
Absolutely, yeah. So this is always, you're drawing up. So
And you could take that same drawing, it's the graph with the arrows that's connecting it.
Yes.
Actually arrange those in any sort of 3D thing. All
Absolutely,
you're doing here is visually putting them in the.
Exactly.
And I do
Yes.
think by and large, the brain is taking sensory information and forwarding it. to
Right.
the motor out.
so there is a sense in which things are feed forward on the large scale. And there's some degree of approximation to which they're feed forward on the small scale, but it's not exact, and there are regions of the brain where it's particularly bad approximation. Let me speed up a little bit because I want to try to, so this is 1960. I promised I would get to 1986. So another thing you can do, and actually this came much later, although from our modern point of view, it seems like a natural choice at the beginning, is you could have said that the JIJs were completely random. And these sort of random neural networks, as they're called, first of all, they're the subject of a lovely theoretical literature in which you can exercise a lot of the tools that we know from statistical physics. And they also, in some sense, provide a benchmark against which you can compare the performance of network or the behavior of networks that are structured in some way to carry out a particular function. I'm not going to say any more about that. Let me now get to what John did. So another way to simplify, right? One way to simplify is to assume that the matrix is feed forward, and another way to simplify is to assume that it's symmetric. So this surely isn't true of real neurons, but again, neither is any of the other things. The idea is we're simplifying and we're trying to plant a flag somewhere in the space of all these possibilities where we can understand what's going on. And it turns out this is enormous, this assumption of symmetry, which was described as Hopfield's great step backward, is what launched the whole field. And the reason is, let me do the case where the thresholds are 0, just to keep things simple. If the matrix that describes the dynamics is symmetric, then viewed as a dynamical system, it has a Lyapunov function, which is to say there's a function you can construct which under the dynamics is always decreasing or constant, which, to use physicist language, is an energy. And so there is an energy landscape across the space of states, and dynamics is flowing downhill on this energy landscape. And the dynamics will stop only when you hit a minimum. Remember, these are discrete variables. So what you mean by a minimum is that if you flip any single variable from being active to inactive or vice versa, then the energy will go up. And so you have this structure, which importantly means that you can say something about where the dynamics will end, despite not necessarily being able to compute. I mean, you could, of course, compute everything along the way, but you don't need to. You can tell me where it's going to end without going through that intermediate computation. So now the question is, well, this is like all the other problems in statistical mechanics that we've seen. Why is anything new going to happen? And so the thing which actually makes it the Hopfield model was the idea of saying, well, suppose that I made the matrix Jij out of the products of binary variables. Now you can see that if you do that, the energy function is just this. So now not only are there minima where the dynamics will stop, but I know what they are. They are the vectors C, the states C. So if that was the only, okay, cute, right? But this is just a ferromagnet. This is just that first Ising magnet in disguise, right? all the spins, all the neurons end up in the same pattern of activity. That pattern of activity, instead of being all on or all off, happens to be the vector C, but there's still only one pattern. And because we set the threshold equal to 0, it's reverse. But you will remember that in high dimensional spaces, most vectors are almost orthogonal. So that means that if I take another vector, then or another one, and I keep going, then the energy function becomes a sum of squared terms in which you take the current state of the network and project onto this vector C. And since we're in a high dimensional space, most of these vectors are orthogonal to each other. And since they're binary vectors, the only way to get a minimum is to actually align with one of these. And then at the point where you align with one of them, the other one doesn't make any difference because it's orthogonal. Sorry, it's not ergodic. So it's not ergodic. You'll stop at one of them. And you don't in principle know which one. That depends on initial conditions. Hold that thought. So what you've done is to craft an energy function, a landscape, that can have multiple local minima, but you know where they are. Furthermore, the rule that you need in order to dig a hole in the landscape at this point is just to ask what state is the system in at this point and make the connection between two neurons stronger or weaker depending on whether they're positively or negatively correlated at this point. It's remarkable because that means that you can sculpt the global features of the whole landscape only by having access, right? Jij only depends on what neurons I and J are doing. So you have a local rule for changing the connections between neurons, which causes the global dynamics of the network to have properties that you want. Okay. Furthermore, to get to your point about ergodicity, you could say, well, you've shown me that you can have multiple local minima. Okay, parenthetically, how many of these can you have? Obviously, you can't have n because then the argument about orthogonality breaks down. So what you can show is that you can have something proportional to n, and you can do a rough back of the envelope calculation to figure out what the proportionality constant is, which is what Hopfield did in his original paper, or you can bring the full power of modern methods from the statistical mechanics of disordered systems to bear on this problem. So imagine that the vectors C are chosen at random, and you want to know the ensemble average of the probability that, or the overlap between one of the configurations of the network and one of these vectors. And so you can build up all sorts of tools for doing this. And when you're done, you find out that John's back of the envelope calculation was correct. I mean, it's a back of the envelope calculation, so, you know, it's roughly correct, but he had the right idea. It is, however, a beautiful exercise in how to use these techniques. So what you've done is to build something in which you have sculpted the landscape so that there are many local minima. You know where they are. Which one you fall into depends on your initial conditions, right? You're going to fall, roughly speaking, into the closest one. So for example, if you think about the state of the network as a whole as having some parts, so neurons 1 through 27 are an image, and neurons 28 through 115 are the sound of a voice, and take whatever other attributes you want that describe your friend, the place you last saw them, and so on. So you concatenate all of these things. If I give you some of that, then what that means is that I can set the initial condition of the network with some of the variables already set to their value at the final state you want. And the other ones are basically random, you don't know. And in that setting, with this landscape, with high probability, you'll recover the state that you stored. And in that sense, this memory is associative, right? It puts the different pieces of the overall state together and allows you to recover the whole state from knowing just a part of it. Okay, 5 minutes? Okay. So why did this have impact at the time? Well, first of all, it did provide you with a concrete dynamical model of something that does the kind of thing that our memory does, which otherwise seems rather mysterious. Okay, it allows for a kind of pattern completion. Okay. It also importantly says that in the state where you're remembering something, it's not because all dynamics has stopped, right? Each neuron, if you think about it from here, if you're in some non-trivial pattern of activity, that's the activity of this neuron, or the inactivity of this neuron, is being maintained by the pattern of activity in all the other neurons in the network. And so that connects to a whole history of ideas about sort of reverberating activity in networks of neurons. Another thing is that not long before this paper was written, people had started doing experiments where you go in and very carefully look at 2 neurons, and you inject current into one of them or the other one and cause them to generate action potentials in different patterns. And before you do that, you inject current into one neuron, have it fire an action potential, and measure the strength of the response in the other neuron. Now you manipulate them in some way, and then you pause, and then you do the same experiment again, and you discover that the strength of interaction from one neuron to another has changed. This is called synaptic plasticity, and it's an experimental phenomenon. Furthermore, it has roughly this flavor. That is to say, at many synapses, the change in activity after some amount of time is related to the correlation between the activity of the pre- and postsynaptic neuron. And that's called Hebb's rule, and it actually goes back to an idea that the psychologist Donald Hebb had in the middle of the 20th century. And if you read carefully, you can find the same idea in William James's psychology book from the beginning of the 20th century. So one more thing, right, is that you realize that what's happening here is you're taking a computational problem, which is to recover this memory. You're solving it by building a dynamics which does the solution. So you're taking seriously the idea that computation is a dynamical process. And I might note that computation is always a dynamical process. And even in your digital computer, the underlying variables are, of course, continuous. And in the presence of noise, which by now in your digital computer is almost 0, but never mind. If you go back a little bit, it wasn't 0. The way you make sure that you get to the right answer is by restoring the trajectory against these perturbations. In particular, by restoring that you're either representing a 1 or a 0 and not any intermediate voltages, because if you did, then things would drift off. What happens here is that the restoration is global. You're flowing downhill on a landscape. If somebody randomly gives you a kick to the right, you eventually still find your way to the bottom of the valley, right? In order to get out of this, you'd have to be thrown all the way back over the hill. And so the robustness of the computation is a global feature of the dynamics, which is a different view than the one we usually have of computation. Let me make one more observation and then I'll. The other thing is that because it's an energy function, what you're saying is that the way to think about computation, in many cases, not all of them, is that the thing you're looking for is the solution of some variational problem. What you then do in order to solve the problem is you build a dynamics in which the objective function, the thing you're varying, is the energy function or Lyapunov function of the dynamics. And then you'll be guaranteed that the network does this. And this was at a moment where people were starting to think about computational problems more generally, including the kinds of computational vision problems that were in Jeff Hinton's thesis, in terms of these energy functions that combine the different constraints that you're trying to satisfy. It also emphasizes that this is, after all, a statistical mechanics problem, right? And so it emphasizes that there's a connection through this idea of finding minimum energy states between computation and statistical mechanics. That means that maybe you can solve computational problems with tools from statistical mechanics. And some of you may have heard of simulated annealing, which is basically take the Monte Carlo methods that were developed to solve statistical mechanics problems and adapt them to cases in which the energy function is purely a computational construct. And this also led to analytical developments where people started to use ideas from take the statistical mechanics formulation of classical computational problems like the traveling salesman or satisfiability and so on, and demonstrate that things which are natural questions in the context of statistical mechanics, like the existence of phase transitions, are actually connected to the results about computational complexity. So part of the reason why Hopfield's work was so impactful was that it sort of created this nexus between things in neuroscience, things in physics, things in computer science, and all of a sudden people kind of had permission to float among these different fields, take the language from one and move it to another. You had a question.
Yeah, maybe a question we took a lot of answers, but in this model where you can predict.
Yeah.
It seems that you know if you can, and you know, and so.
Sure.
And so how much is that not knowing and having an effect?
Well, so interestingly, in some sense, the thing you want the network to do, which is to store patterns. So one way to think about what's happening is you're walking through the world and you have this interconnected network of neurons. And every once in a while, you see something you'd like to remember. And so you send a little pulse that says, change all my synapses now. And the way you should change them is based on the correlation between the synapse between neuron 1 and neuron 7 should change based on the correlations between the activity of neuron 1 and neuron 7. And now you keep walking, and you do it again, and you do it again, and you do it again. And as long as you don't do it too much, so that you don't overwrite your memory, which is another interesting problem, you will end up having stored all these things along your path. And nobody needs to know anything global about the network. If you want to read out the information, you could say, well, I should listen to what all the neurons are doing. But of course, you've stored n patterns in a network of n neurons, not n bits. So you probably don't even need to read out all of them in order to know which one you're in, right? So it really is true that you don't need anything global at all in order to make it work, even how many neurons there are. I mean, in order to do the analysis, of course, you need to decide. But for functionality, there's no place in the functioning of the system where the size of the network has to appear explicitly.
But how it functions.
Absolutely, right. So how reliably you will recall patterns depends on the size of the network and so on. And what's interesting is that, I mean, I sort of was a bit dismissive of the work using very powerful statistical mechanics ideas, because if the only thing you were trying to do was compute your memory capacity, then maybe you should have been satisfied with the back of the envelope calculation. But of course, the really important result of that is that there's a notion of a thermodynamic limit. So at some point, you're big enough that you might as well be infinite. Well, it's like, so in your high school chemistry class, they pointed out that Avogadro's number might as well be infinity. So Avogadro's number is too big for the number of neurons in the brain. But, a small circuit might have thousands of neurons. And thousands is a lot. There are some interesting questions there, but. Well, no, right, that's right. I mean, But you weren't worried about that, right? You were worried about the other end of the system. Let me, now, we're missing one thing, which is that I've told you about. So this is Hopfield's famous 1982 paper.
Can I ask a very quick question? Sir, you kept responding to that, Enrique, and others, that there is, depend, where you end up depends on the initial conditions.
Yes.
This is assuming the dynamics itself does not steer towards the single, kind of like very boring dynamics.
Yeah.
Which may get stuck because of the glassiness anyway.
And so part of the point of this, as long as you don't exceed your capacity, is that it's not glassy.
Not glassy. That's important.
That's
They're
important.
comfortable to know that.
Yes,
Um,
yeah, absolutely. So when you write down models of this form, right? If the J's are not all of the same sign, you expect, so if you can have loops that are frustrated, you expect, generically, if you have J's of conflicting signs, you expect that you'll have frustrated loops and there will be many local minima, but in the glassy way, where you could just get stuck in kind of random places. So the important point is that if you choose J's in this form, this is very non-generic. The X's themselves could be random, but this is still very non-generic in the ensemble of random matrices. And as a result, it's not glassy. There really are only minima at the places where you put them. Exactly. So that was the thing that I was sort of pointing toward with that last slide, that in the mean field spin glass in the Sherrington-Kirkpatrick model, you have many local minima, but you don't know where they're going to be. And in fact, they're a sort of obstruction to the dynamics. I mean, that's a kind of extra statement, right? Because strictly speaking, if you just talk about the energy function, you have to tell me what dynamics are. But any reasonable dynamics will be obstructed by all these local minima and the barriers between them. In the Hopfield model, in contrast, you sort of slide into these. It's a very strongly correlated disorder, right? If you think about it, well, it's interesting because you can choose the X's to be random binary vectors. So that's, each one of them is n numbers. And you can choose k of them with k proportional to n. So that's alpha times n squared numbers, which are random binary numbers. But if you chose the, so that's almost n squared, but it's really not n squared in a very important way and in a very structured way. So let me do one more thing, which is that we talked about these dynamics as if they were deterministic. What if you have noisy dynamics? Well, what you might then expect is that in this model, which has an energy function, maybe instead of just going downhill on the energy function, you'll do something like Brownian motion on the energy circuit. And so then what you'll end up with is that there's a probability distribution for the configurations, which is just the Boltzmann distribution. So the idea that Hinton and his colleagues had there's a couple of different versions of the paper. The idea that they had was, let's let the states of the network represent states of the world. Which is a little different from remembering something, right? In the Hopfield model, the states represent particular things you were trying to remember. Here you're saying more generally, I want the states that I pass through to represent states of the world. But now you have a problem, which is that the states of the world probably don't come out of an Ising model. I mean, it's powerful, but it's not everything. So the idea they had was that as you think about these networks, you want to think about the variables as coming in two flavors. And in the simplest case, you're allowed to connect them any way you want to. Now, it turns out it's useful to restrict that, but you can connect them any way you want to. And the idea then is that it's the states of only the blue part of the network that represent the world, the states of the world, and the other ones are just there to help. So these are called visible versus hidden units. And it's a very familiar idea in physics that when you average over some degrees of freedom, you induce effective interactions among the other degrees of freedom. And so in this case, what you'll find is that although the microscopic interactions are only between pairs of neurons, the effective interactions among the blue neurons, once you average out the black ones, are of course some subset of all possible multi-body interactions. And the important point is that there is a rule, again, for updating, for learning what the correct values of all the connections are, just like there was over here. But there's a way of adjusting them so that the distribution over the blue states becomes as close as possible to the observed distribution of the variables in the world that you're trying to represent. And it really isn't that much more complicated than this. Okay, it's again based on correlations. So the connection between neuron I and neuron J should be changed in ways that are related to the correlation between neuron I and neuron J. You just have to measure those correlations both when the network is running free and when it's receiving input. And the important part of this is that you can interpret this in two very different ways. One way is to think about the blue neurons as actually taking input from the outside world. So their states become the state of the outside world. And then the black neurons kind of process this and extract features from it. And you can interrogate the black cells and ask, what's going on? What is it that in some, that their activity, their variables become something like causes for the states of the blue variable? And this becomes even clearer if you restrict the patterns of connections so that there are no interconnections among the blue neurons. Then in that case, the only reason that this neuron becomes correlated with this neuron is because they were both listening to this one. And so in some meaning, and there's a meaning to the idea that what this neuron is doing is the cause of the simultaneous activity of the simultaneous occurrence of these states in the world. So that's one view, but then the other view is just let the network run, and then it will spontaneously sample a distribution of these states and synthesize for you samples from the state of the world. And so maybe this is a good place to stop because it illustrates that when you think about these network dynamics, you can always look at them in two different ways. One is as a machine to analyze the data that you're taking in from the outside world, and the other as a way of generating samples that come from the distribution of things in the outside world. And I think you're all familiar with how this plays out in modern AI, that you can both you can analyze text, for example, translate it into another language, but you can also generate text. And maybe it's even more charming to think about images. So this was called, for obvious reasons, the Boltzmann machine. And I think one thing I want to end with is there was, part of the reaction to the Nobel Prize was, is this really physics? I don't know, maybe it's neuroscience, maybe it's computer science. So one response to that is a very practical one. I recommend, for instance, that you go read John's 1982 paper, and you read computer science papers from the same era, and you read neuroscience papers from the same era. And if you think that this is a computer science or a neuroscience paper, good for you. Right? It looks nothing like it. And the intellectual style is so evidently the style of a physicist that I don't really think there should be a question. It's a little more complicated for the Boltzmann machine. But where interestingly, in some way, it rests much more on conventional parts of statistical mechanics, but the language is a little less obviously that of a physicist. The last place, the place to really end this part, is that Hopfield chose a title for his Nobel lecture, which was Physics as a Point of View. And he remarked that also in other places, that he grew up with two physicist parents. And his summary was, physics was only incidentally subject matter. It was the way of thinking about things. It could be your bicycle, it could be the sun, it could be an atom. But there is a certain kind of understanding that we're searching for as physicists. That you should be able to take the system apart, that you should be able to understand how it comes back together and so on. And that this should eventually be quantitative and connect to experiment and so forth. And it is that point of view which defines physics. And if you haven't seen the quote, I recommend it to you. It's very elegant and I think expresses the sort of concrete answer to this issue of where the boundaries of physics are in a very elegant way. So, thanks.
We need a 1 minute break. Should we just?
There's coffee out there.
There is coffee out there. So well, let's take a 3-minute break. Bathroom and coffee and everything. Yeah. On the website. You go, when you write the website, you can just go on the website. It was a problem, yeah, and yes, and if you look on the front page, there's a Zoom link that's working.
Click on the button that's going to put that information.
So when I send you this in there, well, if you just go to the front page.
You have time, you can just later.
There's some coffee. But I can figure that out. That's not a problem.
So when we call it this.
So I think sort of all of the above. Actually, more Northern they were but actually eventually one of them, but
I've never heard of them, but
yeah. I would have to know more to read about the context more fully. But I think one of them is actually an MD in position. Yeah, let me answer your question. Oh, thank you.
What's fun that you know I was part of that LinkedIn messaging about the Nobel Prize. So this is what we are.
Yes.
So I tried to reply that
Yeah.
you know it's more likely to out of an hour right.
Yes.
So I'll go back and say
Okay.
for your information.
If you send me a note, I can also.
Yeah, that's what I mean.
What do you think?
Yes. I thought you walked in together. Yes, okay. Good. Yeah, I'm happy to send it.
No, I'm. Oh.
So, so the idea is.
I don't want to mess it up,
Yeah, I
but
don't
yeah, what does?
I think that's
No,
just,
that's for controlling.
Yeah, exactly.
Okay.
Oh, thank you.
This is for the camera.
So,
This is for the camera.
Yeah, let's talk about. Okay, so you're saying you can control.
All right, are we still recording?
I think so.
Wow,
Okay, so you can store.
I have to say that as mine.
And Mike.
right.
No, what I was gonna. Take it over.
Great. Okay, so my job here is to show you how we got from 1986 to the present. And I thought I would start with an interview that Hinton did with the New York Times just after the prize, where they asked him directly that, you know, this prize is for the Boltzmann machine, and, you know, is it safe to say that the Boltzmann machine was a dead end for AI? And his response, I think, is pretty interesting. And he said, I think of that idea as something like an enzyme. And, you know, it got us over this barrier of how do you train deep neural networks, made it easier to train them, gave us confidence that we could train them. And once we'd learned how to train them properly, we didn't need the Boltzmann machine anymore. And so what I thought I would start with is, you know, try to explain to you why we needed them and why we don't need them anymore. And then I have a couple of slides on, you know, where we are now, and we can have a discussion on where we think we're going. So I'm actually going to skip 20 years. We're going to jump from 86 straight to 2006, essentially. And there's this paper that came out in Science that really launched the field of deep learning, and I think the branding of multi-layer perceptrons that Bill told you about as deep learning really started around the time of this paper. And so what I wanted to do was sort of explain what Hinton was trying to do in this paper and why it was important. So there we go. Bill already told you essentially about multi-layer perceptrons, but just a reminder that in general, when people talk about neural networks, there are lots of nuances and details, but at a high level, you should think of a neural network as a sequence of linear transformations. Here, in neural networks, people usually use parameters called W instead of J's. So here they're called W, and the thresholds that we had before now become what are called biases B. And so we do this kind of affine transformation, and then that gets passed through a nonlinearity, sort of like the sine function that we had with a neuron spiking. And essentially, what a neural network is just doing this for a lot of units in parallel, and then for many layers. And the idea, so you might ask, why do I need to do this with many layers? First of all, if you don't have any layers and you just go straight from the beginning to something that you're trying to predict, essentially like logistic regression, but with multiple classes, if that makes sense, you can't do very much. So you need to add more computation on the inside. And there's a famous theorem that if you have one intermediate layer, you can compute any function, but it's really inefficient. And if you believe that data in the world is structured in a sort of hierarchical fashion, and you want to sort of sequentially decompose things into features at different scales, then you might want to have a network that has many layers. So that's for a long time been the motivation of why you want a network that looks like this. And Bill talked at the end of the first half about how with the Boltzmann machine you can write down an algorithm, a learning algorithm that will fit the parameters of your function to represent the data. Here you want to do something similar, but instead of just representing data, we want to make specific predictions. So into the neural network comes an image of a cat or a dog, and you want to output a 0 or 1 depending on whether it's a cat or a dog. And so you can do that. That's actually one of the things that Hinton and others had simultaneously done. It's called backpropagation. And essentially you follow the gradient. You take the derivative of your how poorly you're doing with respect to all of those parameters inside the system, and you follow it and you go downhill to try and improve your performance. The problem with this is that at least at the time it didn't work very well, and people were familiar, or were comfortable with optimization problems that were convex, and this landscape that you need to optimize on is highly non-convex, and for practical and principle reasons, people didn't want to do that, and so practitioners had to go around. This is a talk from almost 20 years ago from Jan LeCun about not being afraid of non-convex loss functions. Here's a sort of more recent image of what a neural network loss landscape looks like. And really one of the big major obstacles towards getting these models to work was, in principle, this architecture looks like what we want. And like Bill was saying, you can compare diagrams across 40 years and they don't look that different. And the problem is we don't know how to actually find the settings of the parameters that solve our problem. And following the gradient, following that local information, at least for many years, wasn't working to the extent that we wanted it to work. And so what Hinton and his collaborators did It's an actual network. I don't think I can go into how they get this image right now. Yeah, this is the paper called Visualizing Lost Landscapes of Neural Networks from Tom Goldstein at Maryland. Yeah, there's more nuance also because the structure of the landscape looks different in different places, and but we can discuss that further. So what what Hinton decided to do was take a step back and try to make use of these Boltzmann machines that Bill introduced, and in particular a restricted version that he mentioned, where we now have these two sort of populations of degrees of freedom. The visible units are going to represent data. We want to model the states of the world, and we have these hidden degrees of freedom that we're going to integrate out that will then generate and induce couplings and represent correlations of different orders in the visible data. And so, this is just to show you explicitly that, if you do that, you end up with some complex energy function that has interactions of all different orders. And it turns out that if you had a large enough number of hidden units, you could represent any distribution with an architecture like this. So it's restricted in that there are no couplings between the visible units and no couplings between the hidden units, and there's only one layer of hidden units. Nonetheless, if you had enough hidden units, sort of like that one layer of a neural network, you could represent any function or any distribution. But it could be incredibly inefficient, and if you believe that data in the world has a hierarchical structure and has causes at different scales, this might be a particularly inefficient way to model data. So what Hinton did was he tried to stack these Boltzmann machines, and ultimately wanted to have a network that had many layers in it. The problem with that is if you have many layers that are all interacting, there's a big equilibration problem. And so he tried to avoid that in a particularly tricky way, where he learned one of these layers of this restricted Boltzmann machine. He got the parameters that map you between your visible units and your hidden units, and then he used that as a mapping from data to a representation, and then got a distribution of that representation, and then did that again for a second layer, and so on. The details I'm not going into because they don't matter anymore. But basically what he ended up doing was training up a deep Boltzmann machine that has many hidden layers. And the ultimate, the training objective here was to model data in the world. And his idea was, if you have an image of a cat and an image of a dog, and I'm only training my neural network in this way that we started out trying, I'm giving you sort of one bit of information for every image that you have, right? The only information that I'm adding into my weights is that one bit of whether it's a cat or a dog, and I'm trying to spread that out with this backpropagation thing. But there's a lot more structure in data than just those 1 bits per image. So maybe if we do this stage of learning about representing the structure of the data itself, we can get a lot of information into all of these parameters, and then that'll be useful later on for when we do the actual prediction of cat or dog. So here, he's essentially trying to learn a model that can generate images of cats and dogs sort of randomly. You can't tell it whether you want a cat or a dog necessarily, but you can sample from it, and maybe you get a cat, sample from it, maybe you get a dog. And what he then did in this paper was use that kind of architecture and use all of those parameters that he learned in the service of generating images of cats and dogs, and forget about generating and just use it in that that sort of forward neural network direction to actually predict cat or dog. And then once you've initialized the parameters in that specific way, the learning with just the label of cat and dog worked much better. And that really unlocked the ability to train these networks for a period of years until about 2012. This really gave people confidence that this can work. Researchers jumped on it and developed a lot of new techniques that. Yeah.
Define what is a cat and what is a dog. They'll provide them the feature of a cat and a dog, and you hold and go to their view who is cat and who is dog.
Mm-hmm.
The other one, so you have this many, what do you call it? Many Boltzmann machines that are stacked and feed forward from one to the other. The goal is to generate.
Right. So totally different goals. And it's not obvious that this makes sense. There was a lot of sort of work that was done to try and justify this procedure.
The other one, the brain say, well, they got the perception of the dog, no, then you start to improve the weight. Here, the input, what it is?
It's just images.
Any images.
Right.
That they're trying to figure out cat and dog, and then you are going to use these
They're-
things. No,
They're not trying to figure out cats and dogs. They're just trying to represent the states of those images. And the learning is this thing called the Boltzmann machine algorithm. I didn't want to write it down, but essentially maximize the likelihood of the data.
Basically, there's a whole probability distribution that this is supposed to represent.
Yeah, so this, I mean, forget about this one. Just this is some energy function. It has parameters. There's a corresponding, distribution that it controls, and now you have examples of the data, and you try to maximize the likelihood of those examples with this model. That's all you're trying to do. You're not trying to know whether they're cats or dogs. It's just a mixture of all of it. Then, yeah, it's a funny procedure. So you take this learned model and where they do this in stacks, and all of these parameters are all in the service of just generating images of cats and dogs. But then they turn it around and use it only to go upwards now, to go from an image and get representations at different scales. And hopefully then we can actually pretty easily decode whether it was a cat or a dog.
And you literally erase half of the connections, is it that simple?
So since these are Boltzmann machines, these are symmetric connections. So you don't lose any parameters, but you treat them now as directed connections. Yeah.
Right. But particular, I have a layer here. If this really was a stack of Boltzmann machines, they'd be getting input from this side and from this side.
Right.
But this is now not allowed.
Exactly.
So conditional distribution this way.
Right. And there was a lot of work and discussion about what we're actually doing here and how does it relate to the original doing inference with the Boltzmann machine or not at the time.
And the very last layer that spits out a vision how it is just the graph on this.
That's right.
Yeah.
Or yeah, I mean, here there's some representation at the last one that you stacked on top of here, and now you take a matrix from that and you use that to make predictions. Yeah. So you learn some new parameters to sort of decode from that representation up there. But you do continue learning all of these parameters also. You don't freeze them. You can do that, but you do better if you train it. So somehow this procedure that people used to call pre-training is a way to initialize all of these parameters, on this very complex landscape in such a way that now learning will take off and we'll learn good things. We'll end up in a good place. That was the idea, at least. And I thought I would give,
Two different types of information that's stored in that. So in the stack, it's basically, for lack of a better word, knowledge on how to create images. You know, we call it cat and dog, but it's just like that network is going to create these images that when we look at it, we go, oh, that's a cat, that's a dog, right?
yeah,
You know, we can train it to create flowers or anything else. So there's some sort of know-how or in those, but there's no labeling. There's no recognition that's a cat or dog. Whereas the other is what I, and I love to call it semantic knowledge, is to say this is a cat, this is a dog, which is even apply label. So it's like two completely different layers of information / knowledge.
yeah, I think that makes sense. And you know, it's not, if you had images of cats and dogs and some of them were on sofas and some of them were out in the yard, you could also, instead of having cat dog be the problem that you then try to predict, you could ask it to predict whether they're in the yard or on the sofa, and that's another semantically meaningful thing. And so we made no, you know, we didn't ask it specifically about cats or dogs when we're doing the representation learning. It's just learning whatever is salient.
Things, as it were, versus the labeling and categorization of those things.
Right. Yeah. Yeah.
Very quickly, intuitively, it seems like the space of all images is just vast. And if I had to start training with zero knowledge of what kind of things to look out for, you know, it's just a lot of things to boil down. Whereas it seems like the Boltzmann machine, by choosing those parameters correctly, it kind of like pushes, like it throws out all of the random images that are totally irrelevant because it narrows down to cats or dogs. And so within that smaller space, it's easier to find it. Is this the intuition for why that brief?
I'm not sure I totally understand that, but I mean, one thing I can say here is that if you have an exponential number of hidden units here, you can model any distribution. If you restrict it to something linear in the number of visible degrees of freedom, that's a much smaller space to explore, and there's some inductive bias or whatever about the distributions that you're willing to represent. But yeah, I can't say more than that. So incidentally, I thought I would also mention, give a couple of plugs for the ITS here. I was looking through, the history of the ITS, and in fact, the very first ITS symposium series in 15 years ago, spring 2010, that Bill organized, included a talk by Jeff Hinton. I was in the audience, actually. This was the first I ever heard of machine learning, and I probably wouldn't have gone into machine learning without this talk. And he was talking about this procedure. And at the time, this was 2010, so this is post 2006 when that paper came out, but pre about 2012 when we learned some other things that made us that enabled us to train networks without these tricks. So these tricks were very important, but he was already seeing the power and seeing where we were going in 15 years, and his title's learning models with trillions of parameters, which is where we finally are now 15 years later, when these were thousands of parameters instead. So yeah, if you want to know about things 15 years before they happen, you should come to our symposium. So what changed, and why don't we use this procedure anymore? There are a number of answers to that. There isn't any one single answer, but at a high level, there are a number of sort of seemingly finicky, architectural variants and tricks, things like adding operations to normalize your activations at different layers, or having like a highway where information sort of skips, straight to the end of the network. And a lot of these avoid information sort of decaying or exploding, not information, sort of activity level, either decaying or exploding as you go through the network. And it turned out that once you do all these things, you think harder about how you want to initialize your parameters. So if you just initialize them randomly, it really matters the specific distribution that you initialize from. You know, all these things are really important for getting, you know, the basic, you know, forward propagation of information and then setting backward of signals to learn from to work well. And it turned out that once you had all of that, and once you scaled up the data, you know, 10x, 100x, 1000x, and in particular compute with using GPUs, this sort of pre-baking that was necessary for those years wasn't requisite anymore. And let's see. So, you know, since then, people really leaned into these bottom two, more data and more compute. So if you ask, you know, what changed to allow us to not need this Boltzmann machine pre-training, it's these things. But now if you ask what changed in the past, you know, 10 years or so, instead of a lot more data and compute, it's a lot more data and compute. And there's really sort of one primary thing beyond that, which is these things called transformers that are based on something called attention. And yeah.
Yeah, to make comment on the transformer attention. So, but we have a study to show them color words. It's called color strip. Right? You know, if you write BLUE with the right hand, we ask you know the ChatGPT to identify the color. You know, if you have long days, the ChatGPT cannot do it at all. So therefore, you know, the attention maximum is not artificial. We call it artificial attention. It's not totally like human attention. That's my opinion.
Yeah, I believe that, certainly. So I've sort of one very high level slide on attention, but I'm not going to go into detail on it. So you know, the beyond data and compute, you know, in some sense, like the main thing that happened in the past 10 years is this attention operation. We can discuss why it's called attention and how it's not like human attention. But you know, if you ever see this diagram, you know, this diagram will go down in history as, you know, one of the most important discoveries in some sense, inventions. And the paper is called "Attention is All You Need." The reason for that is people were trying to add in something that mimicked human attention, looking at a time series and paying attention, focusing in on certain parts of it. But they were doing it in the context of other kinds of neural networks that had a lot of baggage. They were called recurrent neural networks. And it turned out that you could throw away the recurrent neural network and just keep this attention operation. So, you know, the attention was all you needed. And on the right here is a sort of diagram of what attention is supposed to be. So the people that wrote this paper were trying to solve a language translation problem. That's why it's called a transformer. They were trying to have a model that, you know, in came English, out comes French, transform the language. And for that, you know, if you want to know what word comes next, you know, you might need to be, you know, at that moment be having it sort of focusing in differentially on some words previously and less on other words. And you know, this attention operation is trying to do that in some particular way. Let's see. So yeah, but I don't want to go into too many details here. This is sort of a oh, thanks. So, you know, there's obviously been a huge amount of intellectual contributions in the past decade, but if you had to pick one thing, this is the one thing that together with data and compute has unlocked where we are now. And in fact, one of the reasons why this model is so commonly used is that it can leverage data and compute better than other models. And there's something by Rich Sutton who called the bitter lesson that, you know, essentially says, you know, ideas and methods that can leverage compute, you know, will win in the limit. And that's sort of what we've been seeing in the past decade. So, you know, in addition to this architectural variant, you know, I mentioned data and compute. It turns out that physicists played a pretty critical role in recognizing this, and so I think first the first modern version of this is from Jared Kaplan, who was at Hopkins Physics at the time, and what he and others realized was the badness, the loss of my model tends to go down as a power law when I make the model bigger, when I add more parameters, and when I add more data. And it turns out that when you want to train a model, the amount that you have to pay, whether it's joules or dollars, is proportional to the product of the size of the model and the amount of data. And so you might say, you know, I would like to get the best model for the cheapest cost. And, you know, you can imagine, solving that and finding what, how I should increase my amount of data and how I should increase my model size. And, so for example, on the left here, what they did was they fixed the compute budget and increase the model size and then decrease the data correspondingly for each color. And you find a minimum here at the sort of best you can do with that compute budget. And you see you can get better and better as you spend more compute. If you solve this for the optimal scaling of data and model size, you get these nice power laws over 2 decades. And here they're doing experiments on 10 to the 21st flops when they really ultimately want to train a model with Avogadro's number of flops approximately. And if it costs you $1 million to train the model that's the rightmost data point, it's going to cost you $100 million to train that model. You really would like to know that it's going to work. And so these scaling laws were really important, convincing people that had the money to be willing to invest in these big runs and believe that they're actually going to work. Empirical parameters to fit. What do they actually look like?
Their numbers. What are their numbers?
So I trust myself to do it. In other words, you would think that the most important thing is to try to get these output data to be larger than they are now.
So I don't. It depends on details. The original paper from Jared actually argued that you should increase the amount of data, the number of parameters faster than the amount of data, which sounds a bit crazy. And the later paper from it's called the chinchilla scaling laws. I don't know why. Found that these scale about 1-to-1. So you should have for every new data point, you should add 1 parameter. Yeah.
So these loss functions are for which problem we're translating in French or which part of
So yeah, I forgot to mention this. So this is now not doing translation. This is where we are just trying to predict text. So we have some words, and we want a model that inputs those. It has input that sort of paragraph, and it just predicts the next word. And that's the whole objective function. And if I want to say more about this, so there's a sense in which what you're doing here is not supervised. You just have data. You just have you scrape the internet, and you're just trying to predict the next word from everything on the internet. You're not saying, oh, this is an image of a cat, call it a cat. You're just trying to predict what comes next. So people call it a self-supervised objective. So you don't need humans to go label all the data.
So it is a function of a string of words, and you want the next one.
Exactly, yeah.
But so at the end, it's a function of numbers, vectors, and you want to predict the new vector.
Yeah. So
Function on Rn, it can bring out. Forget about words, they are functional.
yeah, I'm being simplistic. You don't use words here. You use what are called tokens, and you embed the tokens. Yeah, each token gets an embedding vector and so on.
Okay, but do they know how is the structure of this space in a certain way? Because at the end you want to, now you have some function, let's assume that this is a perfect function that do this. Now you could have what is the perfect function? Doesn't matter, it's a neural network or transformer, anything. You think their function from Rn to some Rm, a bunch of vector, and the image will be another vector.
Mhm.
Those transformers are going to generate one of those functions. So when you have the optimal function, is it reasonable to talk about that?
Talk about the optimal function.
That exists, but the problem is, neural network at the end they want to do something. But something what is a function. So from one space to another space. And the space will be extremely complicated. Then you want to interpolate the function with someone that's created with certain structure.
Hmm.
For example, you want to have a mechanical problem. The question is, well, maybe it's Hamiltonian, and the question is, can you reveal this Hamiltonian using neural network? And the question is, in language, where you transform basically words into vectors, inside creative space. Does it make sense, the problem of predicted next word as the function of this process?
I don't know. I'm not sure.
Can I ask
Yeah.
another question about the power law feeling? Does it remain power law even near the tail? In other words, like you have it translate English to French or whatever, and then it's slightly off with like something looks like it's not perfect. And then you keep trying to improve as the scale is for power law. So like the cost only keeps increasing as the power doesn't get exponential even when you're trying to protect at the end.
So there is an irreducible error that we're approaching. So
Oh, I see.
I think the regime that most of these models have been in are still in the power law regime, mostly for next token log probability, which is a very simplistic measure. But so if you use other sorts of measures, you won't be in a power law regime. But for that next token log probability, I think we still are.
Yes, another way of running the question, you emphasize that this analysis was done some time in the past before the most recent push.
Mm.
So it provided motivation. Was it actually quantitatively correct, or can we not find that out because some of them were doing?
So I think we don't know with some of the latest models. I think even more than whether or not these power laws hold exactly, this is sort of asking the wrong question. This is asking how much will it cost me to train my model? But if you're OpenAI and you're serving 400 million people a day, you also care about how much it costs to run the model. And so you want to bias yourself towards smaller models trained on more data, even if it'll cost you more during training, because then when you actually deploy it, it'll be that much cheaper. So there's been a trend since then, since about 2022, 2023, towards models that are smaller, trained on more data. There's also been a number of architectural changes, something called mixture of experts, where you only activate sparse subsets of the model that change the scaling and things like that. So it's really hard to say.
It seems like a very uncontrolled experiment, right? Well, because the data comes from one particular language, from one, I think, presumably if you repeated the experiment now, it's not reproducible because the internet has changed dramatically and so on and so forth. Have there been that seems self-evident to me, but maybe we can discuss it. But my question is that has anybody tried to use these models to predict synthetic complicated data, kind of reality dynamic or whatever dynamics coming out of some, I don't know, equations, rather than
These pre-trained models out of the box using them.
Model. Yeah, to basically just say that supposedly it's not the human language that we're trying to predict, It's just something that looks like language that has some structure and whatever that's produced by some generator.
Hmm.
So it's reproducible, we can go and ask different questions. Who produced one?
I'm sure people have done that a fair bit. I
For example,
right. Any time series.
Yeah, exactly. This model trying to look like a whole potted that.
Yeah.
No, I'm just curious whether these exponents alpha and beta have some interesting kind of like intrinsic values that want to go out.
I think they're extremely data dependent.
Right. That's
Yeah.
what I want to ask, like, what's in the data generator? What structure in the data limits? Right. Anyway.
Yeah. Yeah, I'm not sure I know the answer.
In general, the alpha beta are number bigger than one or less than one. In general,
I don't know. I think usually less than one, but I can think I have a case in mind where they're bigger than one, so I'm not sure.
alpha bigger than one, less than one is very different.
Hmm. Hmm. Yeah, I'm not sure.
Yeah, in numerical, it's bigger than one.
Sorry, the numerator? Oh, I really don't know.
I think from mathematics point of view, that
Yeah, I mean, in these papers, you can look up their fitted numbers for many different settings. In particular, the Hoffman paper. Kaplan proposed a different functional form. Yeah.
So questions about whether or not you could model other things other than predictive text. It seems like that depends upon what all it's doing is physical model of the pattern. So what is relevant is what is the structure of the patterns that being physically modeled. In the case of language, it's essentially linear. Like one word always follows another. Right? You might go back in time, you have the prior 10 words, the prior 100, the prior 40,000 words, but it's still a linear. Whereas it ends like the two-dimensional and so forth. So to
I
answer
see.
your question, I think you could take anything out there in the universe, assign it numbers, statistically model it, but the model and the procedure you have to do is going to have to match in some way or another the structure of that thing you're modeling. Does that make sense?
Yeah, absolutely.
So you can't just take anything and throw it into these particular models because they're modeling the structure of language.
Certainly, yeah. And this is not, these are empirical observations. There's no, there are a couple of papers trying to explain where this kind of form comes from in language. But in general, think of these as purely empirical, and they also didn't do a particularly careful job of justifying whether this function form actually works or not. The main goal here is to make sure that you can get the buy-in to train the bigger model.
You have another data. If your data is structured, meaning that what you said, right? You know what the data is about, then you train the algorithm on the data. And then the algorithm produces the answer to predict if you give similar data at another time.
Mm-hmm.
So, somehow I don't get some of the question. Because I'm working on this moment, right? So, and data, but we give the model and there's a lot of data. Mortality of people in the United States from 1980 to now, 2020. Then you leave some data out. You leave the data of 21 out.
Right.
Only the mortality to the model, to train the algorithm. So the model predicts what the mortality of the people from what age will be today based on what happened. part of an algorithm.
Mhm.
And we're right, yes.
Certainly. Yeah, absolutely. The other thing I wanted to emphasize here for how these models are trained, again, I really want to emphasize this next word prediction. So there's a sort of supervision happening locally at every sort of time point, if you will, right? You're taking the past and you're trying to predict the next time point, and then you step forward by one, and you predict the past that includes the truth for what just happened and the next time point, and so on. And a way to think about this is if you wanted to train a self-driving car, one way that you could do that is to record people driving and have a model take in the sequence of what happened in the past and try to predict the next action of the person. But the actual car was driven by the human, so it's like the beginning of The Simpsons with the baby going like this, if you remember that. And the model isn't actually driving anything. You're always staying on the path of what the real data wanted you to do. But then when you use the model, now it's actually in control. It's actually driving. And the reason imitation learning usually doesn't work in what's called reinforcement learning is that you get, if you now let the car drive autonomously, if you get off the path of where the teacher ever was, it has no idea what to do. It never saw any data. And so it's number one, it's surprising that this works at scale with these language models. But number two, if you load one up that isn't post-trained sufficiently, it will sort of go off the rails and start doing wild things because you've gotten off the distribution from which the actual data comes from. And so there are all sorts of things. The model predicts a probability of every next word, and you can restrict, and you have to sample from that. And you restrict the sampling there to only take the top 10 possibilities. You sample from the top 10 or something like that to not by chance get a really rare word that's going to suddenly take you off that data manifold. Yeah.
Because whether to take it a little bit off, so it seems like the important element here is to have a model that is able to say, I don't know.
Right.
So when it gets off track, that it can recognize it, but that's not a trivial task, right? Because it doesn't have the ability to know that.
Right. And so I'll mention one thing that comes next for how we've sort of left the world. The latest exciting work is leaving this next word prediction paradigm, and maybe we'll get us towards being able to say, I don't know.
The probability of each word correlated to the string.
Right. Yeah.
So you're not generating the next word, you're generating the distribution of probability.
Right. You output a probability of all the next words, and
Okay.
the loss function is the log of of the true token or the true word, the log of the probability that you assign to it.
So it's the function, so whatever the component is, the function that is coming from the string of numbers and this produce the distribution of probability.
Right. Yeah. Okay. So, these scaling laws were extremely important. The Kaplan 2020 paper also came around the same time as GPT-3. So these scaling laws motivated the development of GPT-3. And I wanted to do one more promoting of the ITS. We had a lecture in December 2020, and here we had Jared Kaplan telling us about these scaling laws in GPT-3 5 years ago. So again, you should join us for our symposium. Yeah, question. The colors are varying amount of compute. These are flops of compute. And it's a sort of funny chart where for any color, you're varying the number of parameters, and then varying the amount of data that you train that model on by this formula. This CNOT here is 6 or something like that. Yeah.
How much of the structure that in the next word prediction comes from how the language is arranged in the like you arrange the language, the tokenization, can you mess with the tokenization in some way that can alter the process?
It's a good question. I don't know the answer. So yeah, I've sort of avoided talking about this thing that you have to do when working with languages right now, which is called tokenization. And there isn't one unique way to do that. And I don't know how tokenization affects those results.
That gave us the ChatGPT, what happened? How did you come up from saying, I mean, 80 something? We knew this, you know, that something really happened, something we understood.
Yeah, so I'll say two things. One is more scientifically interesting, which is that when you make the model bigger and you add more data, to get lower loss, better performance, you could ask what's happening. And it turns out that the model sort of exhibits emergent behaviors as you get bigger and bigger. New things happen. And one of the things that's really interesting that happens is something called in-context learning, where now in the history that you give it for predicting the next word, you can give it instructions or examples of what you want it to do that it's never seen before, that was not in the training data, and it sort of learned to listen to you and adapt accordingly. And this sort of, you know, when I started working in machine learning, you were always very careful to call it machine learning and not AI, because AI was kind of like, and you know, then it's shifted and you called it AI, and then people would say AGI for artificial general intelligence, and that was like, and so the G there is the general piece is that in context learning. You know, that these models can do general things beyond what they were trained to do. And so that's important if you know, for ChatGPT, you can ask it all sorts of things. But even if it didn't do that, it would still be very useful if it sort of had everything on the internet at your fingertips. So it's sort of natural language interface to the internet. And what made ChatGPT work so well actually has nothing to do with this. So you know, imagine you did this, you got this big model. If you tried to load it up and play with it, it would say all sorts of crazy things. It would often yell at you because, you know, basically it's trained again on the whole internet. And if you poke it, it'll sort of pick a voice from the prior distribution of the internet and behave in that way. And, you know, there's a lot of, you know, people yelling on Reddit or whatever on the internet. So it might, you know, you might not get a model that you are happy with. So what you do after this is called post-training, where you find ways to sort of encourage certain voices and discourage other voices. And so OpenAI figured out at the time a novel way to do post-training, and you know, have it follow instructions and sort of gate it to behave in certain ways. It's still possible these days to jailbreak the models, and if you prompt them the right way, you can bring out that sort of like raw sort of personality, which is very weird. Yeah.
How important is tokenization when training the model? I think in the stream when we first came out, there were some problems with how you want that, like consulting to do everything, and then kind of sit out on them.
Yeah, so it's not as, so the famous story with tokenization, and then I'll finish up, is so tokenization is a way to break up language into chunks. It turns out that characters are too small, words are too big, and so you want something that is somewhere in between. I won't get into why, but you train the tokenizer on data, and it turned out that the original ChatGPT, the tokenizer was trained on some you know, chunk of the internet. Then the GPT 3.5 model was trained on a different chunk that did not include the chunk that the tokenizer was trained on, which meant that the tokenizer created some tokens that never existed in the actual training. So those tokens never got any data, so they would just behave in really weird ways. And it's kind of a funny story. The reason that these tokens existed was they pulled from Reddit to do the tokenizer training, and there was a token that was the sequence solid gold magic carp. And they were trying to figure out what this was. It turns out there was a Reddit user named Solid Gold Magic Carp on a subreddit where people were trying to competitively count to infinity. And Solid Gold Magic Carp was winning. And so there were so many examples of Solid Gold Magic Carp in the data set that it gave it its own token. And so the original ChatGPT, if you said Solid Gold Magic Carp, it would go haywire. They've since fixed that by having the tokenizer training be a subset of the data that the model is actually trained on.
Talk about the post training. Is this where the reasoning that appears now?
Tokenization is different. It's actually before training.
Yeah. After all the reasoning, everything that they're trying
It's a little bit different. So there's post training that includes this reasoning stuff. That's actually the last thing I wanted to tell you. And then other kinds of post training for encouraging and discouraging certain kinds of behaviors. Yeah. So the last thing that I wanted to tell you about was in the past 6 months or so, there's been a sort of step change in both the performance of models. You know, if you haven't used these models in 2 months and you come back, they're qualitatively different than they were a few months ago. And the idea here is the scaling laws that we had here are about how much compute you have to spend to train the model. And now people are finding ways to spend compute when you are actually running the model. And so OpenAI released this O1 model back in September, where they showed that, you know, if you increase the amount of compute that you were willing to spend during inference time, during the actual deployment time, you can get much better performance on hard benchmarks. This is no longer a scaling law; it's a log linear, it's exponential. So you have to spend a lot of compute to do this. They didn't tell us. We don't know. But so for a number of months, this was they said sort of vaguely that they're using reinforcement learning to, you know, encourage this kind of behavior. And the basic idea is to have the models think for a while before they actually commit to what they want to tell you. And they have a way to dial up and down how much they have it think, which, you know, we don't know how that works exactly. But you might have heard about DeepSeek in the news in the past couple of months. There are a number of things that they've done, but in this space, they released a model and a paper describing how they trained the model for how they got this kind of behavior, spending more compute during test time to get better performance using reinforcement learning. And so the idea here is, before we were talking about next word prediction, all sort of very local supervision, all mimicking the data on the internet. So, you know, you might be skeptical that, you know, creativity could emerge from that because it's just learning to regurgitate what's on the internet. Now with reinforcement learning, and in particular, what DeepSeek showed was that they can do this with what's called output rewards only. They can ask it, you know, a math problem, and it can work on solving it. And at the end of the day, it gets it right or wrong. And if it gets it right, you encourage everything that it did to get it right. And if it gets it wrong, you discourage them. And what they found is that if they do this, the model learns new sort of like behaviors or discovers new behaviors. You know, it can self-reflect and say, oh, I was wrong, or that's an aha moment that, you know, that I can use later. Here it's not mimicking text anymore. It's just, you know, learning whatever sequences of tokens are useful to get to the answer. And if you do this at scale, new sort of things emerge. And you know, this allows, you know, this is very exciting for a lot of people because it allows these models to eventually go beyond what people can do. You know, the models like the AlphaGo and variants thereof were trained in, you know, ways that involve reinforcement learning ultimately, rather than mimicking the way humans played. So this is both, you know, very promising, but also a little scary. So, you know, because, you know, who knows what they will discover.
and I think that we go certain section of interconnect is a good number. They have some curation of what is better to train them.
You're talking about this reinforcement learning or this?
Yeah.
This one. So you're absolutely right. In a couple of reasons and in a couple of ways. If you have data that is of varying qualities and you can tell that, you know, if you keep training into the tails of your quality, at some point things will get worse. It also turns out that even if you have good quality data, you can overtrain if you want to later post-train to do something else. But it's a little bit too nuanced. So, you know, taking this this idea of sort of reinforcement learning and what people call test time compute to the extreme. This is the last thing I'll say. There's this benchmark called the ARC-AGI benchmark that was initially designed to be, you know, something that is easy for humans but hard for machines. And then 2 months later, the machines killed the benchmark. Yesterday in the New York Times, there was this article that you can check out and you can try to answer the benchmark questions yourself. But the idea that this comes from this ARC-AGI website, where they benchmark different OpenAI models that were trained to spend different amounts of time thinking before they committed to their answer. And the human level, the average mechanical Turker is about here. You would pay them $3 and they would get 75% accuracy. And now we have models that you could spend 10 times more. You can spend $30 for them to solve the problem, and they'll get the same performance. Or you could spend $3,000 and it will get better performance. And you know, right now we're seeing, you know, these numbers move up and to the left, and you know, we'll look over that. They're sort of geometrical puzzles. I recommend checking this out. They give you they're sort of like geometrical analogies. They give you some color. You know, it's all sort of squares of colors. They give you sort of input target, like 3 examples, and you're supposed to fill the 4th one. But there are a number of interesting benchmarks that these models are getting much better at right now. There's the frontier math that you might know some about, and you know, so we're now in this world where we have a new knob, which is not how much you know, do we pay to train the model, but how much do we pay to deploy it and have them get better. And this isn't, you know, sorry.
Benchmark for smartness.
Right. Yeah. And let's see. So, you know, this is promising in the sense that, you know, right now you get an answer from you know, Claude or whatever, and you don't know if you can trust it. But now with these reasoning models, they have this internal thinking process that is usually hidden from you, but in many of them you can reveal it, you can look at it, and you can see if you believe it's reasoning. So you don't have to just, you know, trust that it got the right answer. You can sort of vet it yourself. Right now it's too verbose to do in practice, but I think that's a promising direction for them to be more trustworthy and you know, for us to be able to vet them as we're using them. So I think that's all that I wanted to tell you. I know we had a lot of discussion, but I'm happy to continue. I think that's right. I think that's right, yeah. And there's a new one also from like 2 weeks ago. So there were sort of now 3 DeepSeek releases. There was one that came out around Christmas, and that was called the V3 model. And this is the model that a month and a half later, everyone said, oh, sell NVIDIA stock because of this model. It actually came out over Christmas. And, you know, they, you know, introduced a number of efficiencies for training. These very sparse mixture of experts that I was talking about, multi-token prediction, all sorts of stuff, and just very good engineering. So, models that we thought cost $50 million to train on the final run, they spent five or $6 million on the final run. So people were very excited by that. That was the original model from Christmas. Then in January, they released this paper, which took that model and then did reinforcement learning on top of it to make it reason. 4 days ago, they released an updated V3 model that has better post-training. So the original one was, a very good sort of raw intelligence, but it wasn't that steerable. And so they spent some time polishing it essentially. So it's a post-trained version of the V3 model. Open source is a nuanced concept with these models, but the parameters and the architecture you can have. A paper for how they trained it is available. The data is not, so you don't know what data they use.
And in terms also, how much money do you need to run one of them?
If you want to run it in full precision, then you need infrastructure to have multiple GPUs. If you quantize it sufficiently, then you could run it on a single GPU, I believe.
So compared to what before you think, for example, the graduate students that want to run science and at least prefer to do experiments. Some version of this one to be reasonable.
Yeah, certainly.
The game change in terms of availability, in terms of application, the result. It would be real time, you have labs that does replicate. Or
Sorry, you're asking, can we use their model or can we replicate? Can we create their model? We couldn't replicate, I mean, unless we wanted to spend most of the GC's budget for that one experiment. Absolutely. Yeah, it's an order of magnitude cheaper, but it's still expensive. Yeah, another order of magnitude. Yeah.
I just ask very quick, what role in, so there's V3, there's the reinforcement, and there is V3 upgraded. Where in that sort of evolution of model, whatever, progression of model is the distillation from? Because, one of the things I didn't fully understand is how do those models benefit from having, ChatGPT? There's this sort of a thing that somehow they couldn't do by themselves. They had to distill from other models that were there before. And I never quite understood like.
Yeah, so what Vadim referring to is there was a bunch of discussion after the DeepSeek paper came out that if you asked it, who are you? It'll say I'm ChatGPT, even though it's not. And the natural explanation there is that they got ChatGPT to generate a lot of responses and use that for their data to train on. I mean, I have no idea whether they did or didn't. The argument against that being why it said I'm ChatGPT is that a whole lot of text on the internet is now generated by ChatGPT. And so if you're just doing common crawl scraping, you're going to get a lot of ChatGPT anyway.
But I guess what I'm asking is does ChatGPT, so is the idea of using reinforcement learning kind of like enough is that a ChatGPT, is that implemented in ChatGPT or is it a DeepSeek innovation?
Sorry.
Because, the way you presented it is that there was a V3, which presumably inherited some of ChatGPT sort of DNA in some sense. But then this reinforcement learning sort of a juiced up version, is that sort of beyond ChatGPT or?
I mean, so first, I don't mean to imply that the DeepSeek model inherited ChatGPT DNA. I think it's unclear whether that matters or not.
Okay, whichever way. I guess what I don't understand is that how innovative is reinforcement learning, like across the different models that are.
We don't know what OpenAI did, but they did make a statement congratulating DeepSeek on discovering some of the things that they secretly discovered, but won't tell you that they discovered. Let's cut this before you put it online. All right, thank you all.
Well, thanks for both Bill and David, and like I said, if you when you find out about the Nobel Prize next year, please think of who would be a good person to continue this tradition.